Well, I say that. So yeah, welcome to the session we've got on research software engineering skills, and we say in Python, but the Python is in small brackets because hopefully what we're going to be teaching today is in Python for kind of widest delivery, but has concepts that will map over in some form or other to other languages. So I'll be joined and co-presenting with Amy Pike, who's here, and Marion Weinzierl, who's there. So we'll hand over after a little bit. So RSE skills, for those of you who are in data visualization yesterday, this is the session where we really get to use the write better code stick. We'll start off with, if you want to follow along these slides, they are on the GitHub, and if you look on the GitHub repo, there's a link on the top right-hand side which will take you to the slides hosted on the net, and you can follow along if you want to copy and paste or click any of the links. Please do. So yeah, we're all here, and sort of we're hoping everyone's nice to each other. Please be respectful. But this is meant to be kind of a session for you to learn, and learn by doing. So if you have any questions, please do just stick your hand up, and we'll get to them. If there's a question you think is silly, don't worry, someone else is probably wondering the same thing. So actually you're doing everyone a favor. And then we'll be making, I will definitely be making some mistakes, and it's possible not all of them will be on purpose. So again, it's a learning opportunity. So if we think about research software, does anyone have something in mind when we say research software as an example? So yeah, so a huge computational model running on GCMs. And indeed, yeah, this is true. So big computational programs, that one I think is CESM, but running on big HPC clusters, something like that. And indeed, sort of, I guess, given our domain, that's what a lot of us are dealing with. But there's a lot more. So when it comes to data processing, this is also software that's being used to generate research outputs, and so deserves the same level of respect. And even when we come down to kind of experiment support, so people going out, gathering data, processing data, there's a huge amount of work that goes into actually cleaning that data. I think we heard on a day, there's been many days, yesterday afternoon maybe, that there's no such thing as kind of raw data to many people. The raw data is often already processed quite heavily into some form that's used within science. So the kind of core tenet of the research software engineering movement is this idea that if you have better software, you can do better research. And so it's sort of trying to drive that symbiosis in some way. So the question of why it matters about whether you're writing good software or not. So this is, I've heard it described kind of in loose terms as the make the researchers brick themselves slide. So this was it was a science article, but if you can't read it in full detail, there was someone who was on an excellent trajectory. It turns out someone tried to reproduce their research. This is why reproducible research is good. And they found out that all these huge claims that have been made to revolutionize their field, Nature papers galore, were all completely irreproducible. And it turned out that the code they'd been written in processing their data, so not running the code, but in the data analysis, had flipped 2 columns of data and completely changed all the scientific conclusions. And overnight, everything came crashing down. So you don't want that to be you. Do we have a missing slide? So the other thing that's important in here is, more realistically, you don't know where your code is going to end up. So what you're writing now may just be the thing to produce the figure that goes in your thesis, or something that you send to send someone as a report on a progress update. But a lot of us are working on big climate models and sort of much bigger systems. We're looking to, hopefully at some point, both affect and effect policy on these matters. And so we want to be sure that we have trustworthy code, reproducible code, quality code. And an example of this, I suppose, would be if we think about the recent pandemic. There are a huge number of pandemic or disease modeling codes that were sort of suddenly accelerated from small individual research groups up to informing huge decisions being taken by governments, some of which were quality, some of which were not quite so quality. So as a more practical example, can anyone look at this and tell me what this piece of code does? It does, more practically. So there's maybe a useful hint here somewhere. We can start to guess. Yeah. Yes. So it's calculating pressure. More specifically, what's the end result of this snippet? Yeah. Alternatively, exactly the same code running exactly the same thing could have looked like this. So if I asked you now what this is doing, it's pretty clear. You can all read, I'm not going to read it for you. But we've got some nice documentation in there. We've abstracted things away into functions. We've got a fairly clear description of these variables, the Boltzmann constant, absolute zero, etc., etc., etc. And then we've got the end output here is pressure average, so we're producing an average of pressure. And so sort of the net goal of today's workshop, I suppose, is to try and introduce to you some tools, some techniques, some things to think about to try and stop you from writing code and slightly hyperbolic on the right, but move towards writing stuff on the left, which is going to be much easier for you to come back to, but much easier for you to share with collaborators, to share with other people. And if you've got other people writing code like this, much easier when they share it with you. So we're going to start off talking about virtual environments. We've had a couple of workshops already, so is anyone here not super happy with the concept of a virtual environment? Cool, so we'll go over this relatively swiftly, but maybe talk a bit more about why we're using the virtual environments rather than just how to do it on a practical sense. So this is kind of a Python-specific thing in a way, though other environments do exist, and if you use something like Conda, this does allow you to have environments with sort of more broader than Python, actually C and other codes. But the idea is it's a self-contained environment in which all the software is sort of isolated from your broader computer. And it's a good idea to use this kind of on a project-to-project basis. And the reason we do this is to stop system pollution, is the jargon word, but this is more to do with, you will be familiar, I think some people might know that NumPy recently was upgraded to version 2.0, and so if you've been using version 2.0 and you've been using netcdf, you've probably found, just as we did in the last week, that everything starts breaking because some things want NumPy 2, but then if you also want to use netcdf, it doesn't work, and Python spits out all of these horrible messages. So if we can have virtual environments, it allows us to sort of isolate these things, install in one localized area a set of software that is all compatible with one another and consistent, and sort of reduce these sorts of problems. In terms of reproducibility, it's also very useful. So as packages go through changes, we get software updates. Some things can change sort of down at the numerical level, such that results you get running code one day with one set of software stack will be different from running it with another software stack. Whereas if you can have a virtual environment in which you actually pin very hard and fast all of those individual versions, then you can go back and reuse that environment, making sure that you do get exactly the same results again. Yeah.
Possible downside with this, like getting too many
Yeah. So this is something I've had where if I'm doing PyTorch things, I'll have sort of 6 different PyTorch projects, and I've installed PyTorch 6 times, and it's huge. It filled up the space on a Mac. But like I say, the nice thing about this is as long as those set versions remain hosted somewhere, you can delete them on your computer, but as long as you have a record of those versions, you can always go and reinstall into a new environment those specific things. So you can move them off your computer, but by keeping a record of them, it's always possible to recover that state. So in Python, oh yeah, sorry. As in on a HPC. By SPAC, do you mean when you have like module load something? Right, yeah. So if you're using SPAC, or some people would call it SPAC, that's a similar way of doing the same sort of thing. So you can actually set the particular environment and the particular, and that's why I say we're sort of delivering these concepts through Python, but a lot of the ideas will map across to other systems. So this is exactly what kind of the build environments on a HPC are doing. Yeah, it's exactly the same idea. Given we're relatively happy, I'm going to go into, and have you got the repo? So if you've cloned the Git repo and we move into it, we're going to set up a virtual environment and load into it, ready to do the workshop. So we do a source in the bin and deactivate, and we can see sort of Python helpfully gives us this sort of little indication that we're sitting in a virtual environment here, which I'll assume everyone is relatively pleased with. Okay, so this brings us to the first exercise in this kind of code-along workshop. So there's not too much to do, but I'd encourage you to work through the code and look through as we're doing it on the screen, and kind of, we won't do everything in full detail all the way down to the minute level, but I'd encourage you to go away and sort of continue in subsequent time. So the sort of setup for this workshop is that you've been doing some simulations with your climate model, and you're looking to improve the modeling of precipitation, and as a result, you've output the results into an etcdf file. And you know that other people in your group have plotted similar figures before, and you don't want to go back, rewrite all of the plotting code from scratch, so you ask them to borrow their code, and they give you a copy. So this is in exercise 1 in the Git repo, and so if we boot into here, you'll see in the RSE skills Python, in the exercises folder, in number 1, which is base code, is sort of this code as has been provided. So what you can do in your preferred text editor, if you open that up and have a bit of a look, we can scroll through, and if anyone has any sort of comments on what they think about that code or what they think the code is doing, please feel free to feedback. And I'll give you a couple of minutes to do that. Yeah, without even being specific, does anyone have any comments or first impressions on looking at that? Oh, it's great. It's great code. We don't need to be here. Yeah, it's got hard-coded file names. I'm thinking more, I'm asking more generally, sort of, if you were given this and someone said, here, it's great, use this to plot your figures, Sort of how do you feel about that? Not enough comments. Not great. Yeah, okay. Yeah, and they're getting in the way. It's like it's harder to read and see what it's really doing because we can't see the wood for the trees. That's fine. We can go ahead. We can run the code, see what it's going to do. So if we go into exercises and exercise 1, we've got here, and if we oh dear. So we've hit the first problem, which is that we don't have anything installed. We've got no NumPy. So this is fine. So we can do a pip install NumPy, which will go away and fetch things for us. And so that's all good. We can try again there. So now we're missing matplotlib. And so this comes back, I think, slightly to a question we had before about having sort of lots of virtual environments on our system, and the idea that no, we don't need to have them persisting forever. We need to just store what's meant to be in there in one place. And so this can be done with, let me see where we were. So this can be done by looking at this requirements file.txt. So in the top level of our code, you can see there's this requirements.txt, and here we've actually specified all of the things we're going to need to run this code. So rather than kind of hazarding a guess and trying to work out, we can do these all in one shot with pip by doing and I should say I've come back up to the top level of the directory here, but we can do a pip install -r, which is saying it's going to look for rather than a single package, we're looking for something that contains a list of the dependencies, and then we're going to give it the name of that text file, and you'll see if we run that, it'll go away, it'll fetch all of those things we specified. And I would say, Amy, we're going to want to look in the files that are output. Oh no, we've got the IDE. That's good. No worries. I suppose this is why people use IDEs. Maybe it's not. Okay. Maybe it's not a bad. And so one thing I would encourage you to do when you're sort of producing code, especially Python code, or if it's on a HPC, is actually maintain a list of the packages, the dependencies you're using, and sort of keep them with the code so that when you send it over to someone else, they can set this up and get going immediately. They don't have to start fighting through working all of this stuff out. And hopefully without saying this will have installed it in the virtual environment, but if we wanted to sort of go work elsewhere, very fine. And you can see here, whilst this just lists kind of things to be installed, what one can do is actually put some harder restrictions in there to say that we need a version of NumPy that's at least more recent than 1.2. And you can go and read up on this, but you can actually sort of pin things more strictly, less strictly to exact versions if you so wish. And this is kind of the most simple way of doing it. There are more elaborate ways of kind of packaging up Python code, but that's kind of beyond the scope of today. So if we go back to the precipitation base code we've got, we can now hopefully run that. Fingers crossed it goes away, churns through and does some things. It's certainly looking better than it was. So that's gone away, and you'll see now we've got a bunch of extra things have appeared in that folder as the result of the outputs of this code. So the main one, I suppose, is to look at the output. So here we've got a lovely plot of the precipitation that we're studying, plotted across land. We've also got the ocean, but the ocean's been sort of greyed out, so it's a nice little plot, exercising everything you'll have learnt in the plotting class yesterday using CarterPy. So that's one piece of output. If you want to have a conversation about a few things, if it's the code, don't worry, but if it's other projects, thank you. We've got a few other plots in there, sort of reasonably inconsequential. We know they've been generated. So something looking at trying to visualize the El Nino Southern Oscillation. We've got a text file. So here we've output kind of a bunch of different countries, and we're looking at how the average precipitation rates over the course of several different years. So yeah, the code's done something, it spat something out, we're all good. So the next thing we're going to talk about is the Python PEPs. So PEPs are short for the Python enhancement proposals, and so this is sort of how Python evolves as a language. So sort of in the beginning there was Python, and Python was fairly simple. And gradually over time, as people found they wanted to do more and more things with the language, the way of submitting sort of an idea was that you wrote an enhancement proposal and it was considered, and then if it was sort of seen valuable, it would be brought into the ecosystem itself. The key thing for us in this workshop is that this is where a lot of the technical documentation is, and where a lot of the kind of guidelines, the standards, and the sort of original suggestions for the best practices of doing things are stored. So particularly relevant to us today are going to be the proposal 8, which is the style guide, which is sort of how you should structure your code, how you should lay it out, how to make it readable. We're also going to talk a little about documentations, and then I said packaging is slightly beyond the scope of today, but is another good one to look at sort of as you become more comfortable with this. So yeah, the first one is formatting, and I think Dominic will correct me, if you boot up Python into a REPL and run import this, you will get the Zen of Python. And one of the things on the Zen of Python, this little Easter egg, is that readability counts. So there's lots of other things, lots of other ideas here. But the key thing, as far as we're concerned, is, yeah, the readability counts. And so what PEP 8 sets out to do is describe how we should be sort of standardizing things in Python so that everyone structures their code in the same way and we know what we're looking at when we come to it. Like I say, this makes it easier to share. People know what they're expecting to receive. In addition, it makes it sort of much easier to read, and we begin to conform to some of those better practices. However, if we have a look at if we have a quick look at PEP 8 with Python, you'll see as you scroll down, it gives you kind of these nice way of describing things of green, this is good, this is how you should do something, here's the bad way of doing it. So there's a whole bunch of these. I'll try and find something that's nicely representable. So here, for example, when we import things at the top of a file, the good way to do it, the Python recommended way to do it, is you import one thing on one line. Now, Python is flexible. Sort of if you do anything in Python, it'll probably work. So you can stick imports on one line, but the advised way is not to do that, and they give you a sort of a description of why this is. But you can see that these guidelines are huge, huge, huge. And let's be honest, no one has time to memorize all of this. The good news is you don't have to, and this is where the first tool we're going to talk about comes in. So Black is what's called a code formatter. So what it'll do is if you run it over your code, it will go in, it will find all the bits where you're sort of breaking the rules or breaking the best practices, and it will fix them for you. And I think the important thing to highlight here is that it won't change the functionality of your code. So it will only change things where where it's going to run exactly the same. So if you've not got enough white space, it'll add that white space. If you've got too much white space, it'll condense it. If you've got lines that are too long, it will break things onto multiple lines. If you've got a really, really, really silly, has anyone played Undertale? Yeah, so maybe you've heard famously the whole script for Undertale was one like 2,000 line if else or if else if structure. So if you've done really, really stupid things or really, really silly ways of writing code, it's not going to change that because it can't be sure to reproduce what you've intended to do. So it will only be the formatting. And there's, like I say, there's an example online where you can sort of see how this would, so there's an example where you can try this online. And so you can see on the left-hand side is kind of what we would call code that will work, but it's badly formatted, it's hard to read. On the right is kind of the result of running black over the code. And so, yeah, you can see how it's nicer. So this is a pip installable module. So if we return to the terminal within our virtual environment, we can do pip install black. It'll go away, it'll pull it down. And then to run this, we go in and we run, to run this, we can then run the command black and then pass it the name of your file. If you have something with multiple Python scripts, then you can run it over all of those files at once by passing in a directory. So, is everyone happy there? Perfect. So yeah, here's another example, sort of my example, like you can see the one online. Yeah, hopefully you can see one of these is much easier to read than the other. So my suggestion would be sort of working to incorporate this into your projects now. And I say that because it moves all of your code into one consistent style that you become used to reading. And then if people share code that's formatted in the same way with you, you're used to reading it, you know what to expect. It becomes a lot easier to start processing and working out what's going on, unpicking sort of the logical structure of that code. Yeah, other things to note. So it's a widely used standard, sort of loads of places are using it. And you can get a version for your Jupyter notebooks as well. You can look at that in your own time. So exercise 2, if we come out of exercise 1 and move into the exercise 2 folder, I'm just going to shut some of these down. You'll see that we start off with the code in a similar state as it was before. So in fact, exactly the same state as it was before. What we can do is we can run black, provide it that precipitation climatology file, and if we hit return, it'll go ahead and tell us that our file wasn't completely compliant, but it's okay because we've reformatted it without any problems. One file's been reformatted, here we go, hooray, let's celebrate. And so if you now return to that code, you should be able to see already there's a slight difference in all of this. Sort of things have been moved into a more compliant structure. There was, like I say, there was a second file in here. This long function thing, what I might do is briefly, no. Okay, so yeah, we can see here this is particularly sillily written. We've got huge amounts of white space. If we now go back and run this over the whole directory, it'll go through, it tells us again, we've now reformatted that additional file, and hopefully it's a little bit clearer now. You can look at this, and it all looks a bit nicer. Okay, so any questions there? Cool. And like I say, this is something that will change the code files, but the key selling point is that it won't change the way your code's working. It won't change the functionality. And at this point, I'm going to pass over to Amy, who's going to talk to us about naming.
Thank you. Hi everyone. So the next thing we're going to talk about is naming for code clarity. And it might sound really finicky and inconsequential, and what does it matter what I call my variables? But actually the idea is to make your code more self-documenting. So ideally what you want to be able to do is look at your code, and rather than have to pick through all the logic or go through the comments, you want to be able to just look at it and read it as easily as possible and know what it does. So here are some kind of tips and conventions to make it so you can do that. So the first one is that the name should show the intention. So when you name a function or a variable, really think about what it actually is, and so that when you come back to it in, say, like a couple of months or a couple of years, or somebody else looks at it, will they be able to look at that name and know straight away what it is that that's doing? The second tip is to use names that you can pronounce. And this might sound really sort of finicky, but I don't know if you've ever read like a science fiction book or a fantasy book, and there's that character that has that name that you just don't know how you say it because it's all consonants. And maybe that actually took away from your enjoyment of reading the book a bit. Maybe you sort of stumbled over it every time, and it just made it that bit harder to read. It is the same in code, and it will take a load off of your brain if you can read it easily, because you want to be focusing on the logic. You don't want to be focusing on, how do I say this thing? So the tip is to, pick something you can pronounce, ideally a real word. And then following on from that, it's good to avoid abbreviations. You don't want to be playing the abbreviation guessing game in a year's time when you're like, what did I mean by pr or an or whatever, unless it's kind of like an accepted technical abbreviation. Ideally, try and avoid that. As somebody said, I can't remember who I'm quoting, but they don't charge you by the letter. And especially with things like IDE, you can use tab to complete, so you don't have to worry about making things too long. It's good to be concise where you can, so sometimes there's a little bit of a balance to find, but generally it's better to avoid where possible. And then another kind of part of that is if you use names that you can search, so if you're using an IDE like IntelliJ, it will make your life a lot easier. So I don't know if you've tried if you go Command-Shift-F in here, you can search the whole project for a particular string of text. If I've called my variable L and I look for it in here, I get a lot of noise. If I've called my variable length, it's a lot easier to find anything relating to that. So the next tip is to choose one word per concept in a given code base. So for example, if you're doing kind of similar functionality, like I've got, say, a database and I want to add different entities into it. If I have, say, students and teachers, if I have add student and put teacher, that will add a layer of confusion for someone else reading the code, because they'll find your add student method and then they'll look for add teacher, but they won't find the hidden put teacher. So if you can pick one word per concept, it will make your code easier to interpret. So we got to plurals to indicate groups. So rather than having to write out dog list, it's generally more concise if you just pluralize the thing that's in the list. Next, so describe the content rather than the storage type. So generally, it's redundant to say what you're storing the object in. You know it's an array because you've probably just written it when you declared it. And also it can be very vague. So if you read array in the code, you've got no clue what's in there. So it's better to say what it's storing. So another example as well, so we've got array. If you say dogs, you know you've actually got an array of dogs. Age integer, that's probably going to be redundant because you will have written like age equal, or like age int maybe if you're using mypy, and then declared it. I thought I saw a hand, but I've completely hallucinated it. And again, like maybe this won't always fit in with what you're doing, but that's probably a general guide. Next up is if you're naming booleans. So the convention is to use prefixes to things that either are like true or false, so is, has, or can, and to avoid negations where you can. So try to avoid using statements like not green for a Boolean, because then you'll find later on when you go to use it in your code, it will make your logic appear a lot more complicated, because someone will have to read if not green and then unpick that kind of, especially if you end up with like a double negative, like if it's not green, what does that actually mean? So yeah, try and avoid those. So there's a couple of examples there. So purple actually is purple reads better in the code because you can say if is purple, whereas if purple doesn't really make that much sense. And then general guiding principle, like keep it as simple as you can, as concise as you can, and use technical terms where appropriate, but also try and make it expressive. I think there's a lot of mathematicians in the room and a lot of people with engineering backgrounds, and I think our instinct, we've been trained to go for one-letter variables and things, but actually you can be a bit lengthier in code. And then the last thing to cover is explaining variables. So this is where you create an extra variable in your code, break it down a bit and make it a bit more readable. It's possibly something that you've done before, but you don't really know what the official name for it is. So in this example at the top, we've got if age less than 14, return 3. In the example at the bottom, we've added this isChild variable. So that's the explaining variable there. And then that just makes it clear, what does it mean if your age is less than 14? It means you're a child. And maybe you could have written that in as a comment in the code, but by having that explaining variable there, it saved you having to do that, and it's made it a bit less cluttery. So here's another example of an explaining, or in this case, we've not got an explaining variable. Can anybody see what this code is doing? A lot of furrowed brows. Does this make it any better when we put an explaining variable in?
I think I can always write on
So it's looking for a phone number, yeah, in that string. Yeah. So for the next exercise, we'd like you to go into exercise 3. If you're using an IDE, that will probably make it a bit easier, but you can use a text editor as well. So if you open up naming, exercise 3, and we'd like you to spend sort of 5 minutes going through and seeing if you can change any of the naming in here to make it a bit more readable. Maybe you'll have to do a bit of thinking about what some of the code is doing and might have to do some guesswork, and I think the idea is to kind of show that actually naming does really matter and can change how you understand the code. So if you can try and find an example of each of these, a bit of a treasure hunt over the next 5 minutes, that would be great. If you're using an IDE, there's a trick. So if you right-click on a variable or a function, and then you go down to refactor here, I can go up to rename, and then type in whatever I like, and as if by magic, it will rename it everywhere in the code. And it's a lot more sophisticated than just using a find and replace. It will actually go through and like work out functionally where it needs to change, and then hit enter. I don't know if anybody in here is using an IDE, but I would really recommend doing so because it does make life a lot easier. So any questions? So just in case you're having trouble finding the slides, if you go into the repo in the readme section, top right. Here. Okay, yeah, thank you. They're just here if you want to access the slides on your own machine. Cool. Great, so hopefully you had a chance to find most of those. Don't worry if you didn't. We'll just take a few suggestions from the floor. So what did people rename and why? Yeah, nice spot. Yeah, stuff file. I'm not sure what that is. Cool. Okay. Yeah, nice. So maybe we could rename that to land surface fraction file. Cool. Anything else we spotted? I'm going to draw on a couple of examples, if not. So first one I'd like to highlight is this D array. So this is an example of naming the storage rather than the content. So it's quite hard to judge from that what it is you're feeding into that function initially without reading the whole of the function. So if you were to call that something more informative like precipitation data, then you would at least know what you were feeding in there. We've got yeah, excellent spot. Yeah, create plot. What plot is it creating? Who knows? Yeah, good one. Nice. Are there any more that we spotted that we want to highlight? Yep, exactly. Yeah. Yeah. Yeah, brilliant. So those are both great examples. So climate is not that much harder to type out, but it means that you don't have to kind of guess at what it's actually supposed to be. And dset, again, is an example of abbreviation. Cool. Okay, so if you'd like to go to the next exercise, the way this is structured, the exercise following the previous one actually is kind of the solution to that. So if you go in exercise 4 and open up the same code again, you can see we've had a go at renaming it to try and make it a bit clearer. And if you'd like to have a look through, hopefully you can see that it has improved the code clarity quite a bit.
Okay, so we're going to sort of change tack a little bit again and go back to formatting. So when we did the work with black, we said we changed the formatting of our code, but if there were sort of structural things or less optimal ways of doing things, then black isn't going to change that because it wants to make sure it preserves the operation. So this is where a second tool comes in, which is called Pilot, and we're going to be talking about. And this is a form of, I guess, the technical term. Previously we had formatters. This time we're having static analysis. So static analysis refers to the fact that it will go through, it will process and it will process and look at your source code, and it will try and flag things about it without actually running that code. So much like the formatting, it sort of guides us towards more readable code, but the other thing it does is it also guides us to writing better quality code, so kind of trying to get us to avoid bad anti-patterns and this sort of thing. So I would say Pilot, I should also mention Pilot is but one tool. There are other options available here. We're using Pilot because I think it's the most beginner-friendly one, but any of these do work, and similarly, we're using Python linters and we use Black, which was a Python formatter. If you go digging, there are linters and formatters available for other languages as well, in which you can do this similar sort of thing. Much like installing Black, it's a pip installable module, so we can do pip install pylint, and away we go off to the races. Okay, any questions? Perfect. So as an example here, yep. So this is a good question. So they both fulfill different things. So what I would usually suggest is if you've got problems with formatting, Pilot will point them out, as well as pointing out kind of code design problems. If you run Black, it will clear away all of those formatting problems, just leaving the design problems, but they're two slightly different tools. Now, one on here that's kind of taking over is rough, and rough is one tool that will perform both of these operations, and it's the one I've now moved to using sort of day to day, but I find there's much more of a learning curve in setting it up and configuring it, which is why sort of introducing these ideas, it's nice to use Black and Pilot. And then once you feel comfortable, you can maybe explore further. But yeah, there are other options. Other options are available. So if I were to take a look at this code here, can anyone look at that and suggest something that's wrong with it, whether it's going to run. No, all looks sensible. Seems sensible, so we throw it at Python. As we chuck it at Python, and Python is going to crash. And this is a pain because it means we then have to go back to our code, open the file, fix the error, go in, find the next thing. So the sneaky thing that was hidden in here is that we pass in param 1, 2, 3, 4, 5, 6. And you'll see down here, when we're using param 2, we're using it with a 2 at the end. So this is super hard to spot. It hides in that code. Perhaps there could be something to be said about choosing better names. But this is sort of illustrative that this is something hard to spot as you scan through the code, and something that you would find out only when you throw it at the machine to run and get errors back. So the beauty of Pylint is if we run Pylint, and I realize the text is a bit small, but we'll come back to doing this. Well, actually, I think we can go to we can go to exercise 4, and you'll see that you've got that long function file in there already. So if we do Pylint and pass it the name of that file, if we can type properly, you'll see it will go through and find a bunch of things that will give us a report that says, oh, hang on, you're using a variable that you haven't defined, param2, and not only that, you're actually not using the variable you're passing in, param two. And so this means that we can run this before we chuck our code somewhere else, and it will help find those debugs. Now, this is fairly inconsequential. Python is cheap. We've got laptops. But think about submitting sort of a large run of a large piece of code on a HPC. You send it off to the queue system. It sits in there for 2-3 hours. It eventually runs, and you get the email back that says, code run finished, only took 20 seconds, and there was some ridiculous error. So what static analysis is doing is it's trying to catch these and trying to point them out before we get there. So this is one thing, is it's going to catch unrunnable code where it can. The other thing is it also tries to encourage you towards writing better code. So we've already had a couple of people mention doc strings, and Marion will come on to talk about this in a little bit, but the sort of it's pointing out to us you're missing doc strings throughout this code, and better code would have these here. One other one that it's picking out is the dangerous default value of double brackets. So if we go back to this code here, it's complaining about passing in this argument here. Does anyone know why this is bad? Come across this in Python before? Yes. I can't see who said that. Yeah. And why, for those of us who aren't as verbose, what is mutable and why is it bad? Yeah. So it's a bit vague, and maybe we don't all know, but you'll see when we run Pylint, we've also been provided a bunch of error codes here. So dangerous default value corresponds to WO102, and you'll find that if you go to a browser and look for Pylint's WO102, we now get a much nicer sort of description here, describing to us in more detail with some examples why this is sort of a bad idea to do. So in this particular instance, passing a list, the expected behavior is that when we call this function, it's going to stick property of the zoo into that list and send it back. And so we can see multiple times we call the same thing, and our expected behavior would be that each time we instantiate an empty list, write something into it, send it back, instantiate an empty list, write something, send it back, whereas actually one of the kind of the gotchas in Python is that when you declare this the first time as penguin, it persists in life beyond the end of that function. And so you can see actually what happens is by calling this multiple times, we're taking the list that's still living and appending successive items. And so hopefully this is somewhat contrived, but you can see how this could be something you do that easily catches out your code. And the big thing here is that this won't fail. This is perfectly acceptable code, but it's not doing what you think it would do. And instead, what you should be doing is passing penguin in as either penguin as kind of default none, and you should instantiate it every time in the routine. And so this is what sort of Pylint is doing, is by saying, this is perfectly runnable code, but it's not what it should be, and it's slightly dangerous. Yes? Yes, yeah. So you can see kind of the suggestion for better code is indeed to define an empty list and then append to it. This is fine, but it's when you're passing it into functions, because what you expect to happen is for it to be destroyed at the end of the function and then start again, but that's not what really happens. And so if you get these warnings, you can always go and do a search, and hopefully it will give you some kind of indication of what's going wrong. And then at the bottom, and I wouldn't pay sort of too much attention to it all the time, but it will give you kind of a little arbitrary code rating that you can see gradually improve. And if you run it, fix some issues, run it again, it'll sort of tell you your code is getting better. That said, I wouldn't aspire for 10, because sometimes it can be more time investment than it's worth. So the other thing I wanted to point out here, and sort of Amy mentioned already about IDEs, is Pylint and the other formatters often have very, very good IDE integration. And the reason I really like sort of using Pylint with the IDE is that rather than kind of writing your code and then running something to see where it's wrong, actually as you write your code, it will give you kind of the squiggly underlines, so you can immediately see what you've done that might not be ideal practice, and it sort of gradually coerces you into becoming sort of writing better software, and sort of you get sick of being told you're doing the wrong thing every time, and sort of you gradually just pick up these better habits as we go along. And so there's integration on sort of loads, all sorts of editors, and I'll just show you briefly on sort of in IntelliJ, which is the one Amy's using. You'll see that we've got kind of some things grayed out here. So in our imports, this is grayed out, which is sort of telling us that this is something that's not being used. This is kind of a hangover that someone has left in the code that we don't need. So we can actually see that we can go ahead and get rid of it. Where else have we got problems? So here, there's a complaint. I mean, this is slightly redundant because this is a comment line, but it's warning us that the line is way too long. There must be some other better examples. Oh yeah, does that? Sorry? No. Yeah, I'm trying to see how do I find the error report from? Is it that thing there? No. How do I get the oh, if I hover over it. Okay, so yeah, you can see as you hover over it, it actually comes up and it gives us sort of the report of what particular rule we're violating and why that's a problem. And so hopefully if what we can experiment with is if I do my func and I give it something like a equals, so you can see here it's told us that this is, oh yeah, so So you can see here that we've got the squiggly underline, and it's giving us that warning that we're passing a mutable argument. So sort of before we've even written the code, defined a whole function, done a whole bunch of things, sort of it's telling us already, don't do this, try something different. Exercise 4 is to go and sort of run Pilot in the code that you've got and sort of investigate some of these things. In the interest of time, I think I'll leave this as something for you to all do, but you'll see when you do this, you're going to get a whole load of things, and some of these are, some of these are easier to deal with. Sort of a lot of them are cleaning up, making things a lot more readable, missing arguments, unused arguments. Some of them are slightly more difficult, and what I would say is, just as a final comment, is this is how PyLink comes out of the box. As you get sort of more into things, you might find actually when it's complaining saying you should have only 5 arguments to a function, maybe writing scientific code, there's good reason to have more. You can tweak these settings with configuration files to sort of conform. We're not saying sort of there is only one way to do things, but the idea is to kind of gradually encourage you into better practice. So I think that's me finished. And like I say, like Amy said, the start of exercise 5 is the solution to exercise 4, so you can have a look through and see some of the changes that have been made in your own time. Okay. Yes.
Is that any?
Right, yes. So you might have been in the GitHub session yesterday, so the intermediate one, and I think they talked a bit about continuous integration. So you can get it set up in GitHub whereby you can apply the formatters and apply the linting as a check. Now, I prefer not to have it do it on the GitHub side, because what happens is if you push up, it applies back and then commits. You then have different code from what's on GitHub. But you can go in and set up kind of pre-commit hooks that will apply it before your commit, or will refuse to take your commit unless you've done it.
Okay, we're starting to run a bit short of time, but we will go back to talk a bit more about understanding our code and readability. And the first thing, and that has been mentioned a couple of times, is comments. And we all know comments are great and we need comments, and people say, okay, I will write comments into my code, and they go away and start doing something like that. They are basically replicating what's in the code already. They might have used good naming techniques and everything, and so, and they are just saying, okay, I'm doing this here, I'm doing that here, and it's basically lots of unnecessary comments, but not necessarily helpful comments to someone who comes in new to the code. Another problem with comments is there's not really any way of checking that what's in the comment is true. So you might have written a comment at some point, and then you go back and you change your code, and then it's no longer, the comment is no longer basically explaining something about the code. So you do have to make sure that you maintain your comments as you go along and update them in the way so that they actually doing the right thing, because otherwise you might introduce additional problems, because somebody comes in and reads your comment and then tries to understand how your code is actually doing what's there in the comment. So some comments that we want to avoid, so something that we do not want to do is dead code. So you might have lots of printfs in your code, you might have old versions of doing the same thing, or so that you've commented out, and so this is something that you should at the pull request stage at the latest actually get rid of, so that it doesn't confuse people reading your code. You do also not need to basically have the running commentary for each variable definition that you have in there. And as I said before, you also don't need to have these very trivial comments that say, okay, I'm doing this, I'm doing this, I'm doing that, I'm doing that. So this is not the type of comments that we are talking about when we say, okay, your code needs comments. So some thoughts on what we actually do want is we do want comments that give some additional information to your code. So you might have written a really efficient function or really efficient thing that sped up your code, but it's now looking awful, or it's now looking very Pythonic, and it's actually no longer really clear what it does. But if you try to unravel it a bit and do something of the nice things that we've heard about, it slows down a lot. So this is the place where you want to go in there and then actually in your comment explain what it's doing and why it's looking like that, and you should maybe not go back and refactor this part. You also want to give additional information in terms of, okay, oh, I've actually taken this algorithm from numerical recipes or so and implemented it here, or I've implemented something from this paper. So you basically want to link back to where you got this idea from, or where somebody might need or might go back to and find additional information. And then also, if you have started writing something but you know, oh, I have to go back when this is done, or so, you can put something about incomplete code bits and why do I do something here, or where do I have to basically go back to and continue from here, basically. And then the last bit here is about comments are not documentation. They kind of are, but we have heard a couple of times now today about doc strings. And that is the place where we really use comments as documentation. And you have seen this in the exercises. You have these triple quotes that tell you then afterwards, okay, this is the function, this is what it does, these are the parameters, and this is how you can use this. And maybe just to, as a little like reminder, what's the difference between doc strings and comments. The comments tell you basically how this code works and give you the additional information, and so while the doc string tell you how to use it. So if somebody comes along and says, oh, I just want to use this function, how do I do it? Then they can go to the doc string and find out what they have to do and how to use this function. This is basically what it looks like. So we have a short one-line description of our function, or so about what is this. Then we go to, okay, what comes into my function, so what is the input, and then we go to, okay, what comes out, and then we can also have some additional things like these are the errors that might be raised in this function, some usage examples or so, or even key references. So to be a bit more specific, this is another example. So we have the description of what my oh, that's really small, is it? Can you read that? There's a description of what the function does. Then you have a description of the parameters. So if somebody comes and wants to use your function, they know, okay, this is my list of parameters. This is the type of my parameters. And then, yes, that's that. And then you also tell them, okay, and this is what you get back when you use this function. And then you can add additional notes, like here you have a reference, oops, and yeah, and then the bit below is the actual code. So your doc string can actually be much longer than the code bit, but it helps other people to use your functions. I think in the interest of time, I'll not do the exercise. But if you go to exercise 5, you can go through there, and there's even a little like, so you can look at the code, and you can look at, okay, are there good comments, bad comments, and then also the doc strings, and then there is PyDoc style, that's the name. The PyDoc style exercise as well, which is kind of a type of linter that you can use for your doc strings as well, if you're interested in that. But one thing I'm really feeling strongly about, and that I want to really emphasize here, is the importance of READMEs. So if you have a repository or your code, then please provide the README, because this is when I go and I want to use your code, so this is the first thing I look at. So before I even open any source file, so I will look for a README, and this README should give me the information, okay, what is this code? So what does it do? Why should I use this code? What problem does it solve? And also, how do I use it? How do I get started? So I want to basically have this easy entry point where I can go and very quickly have my very first example running and know, oh yeah, this is actually the code I want to use. The README you might have seen in the GitHub courses or so are usually written in Markdown, and I've provided a couple of links here that can give you some easy some useful information on what actually a README should look like. But just as a bit of an overview here, so this is, in the best case, what your README should contain. So as I said, I first of all want to know, okay, what is this software? Maybe you can tell me what paper this basically relates to. So has there been some publication, or maybe you have several versions of your software, so relating to different stages or tags in your code base. I want to know, is this code that I can go away with and already use, or do I have to expect that there are a lot of bugs in there? And then we go to, okay, what do I need to make this run? Maybe it has a requirement file in there already, or a spec file that I can simply use and install all my requirements in one go. But if that's not the case, then at least it should list what I need to install to run the code, so that I don't have to go and hunt for all the requirements somewhere. And what I really like is if I can go there and just click this little copy button in GitHub and paste it into my terminal, and it will install all my requirements for me, and maybe even build the code and have some simple example running. Then what is a really good thing to have in your README is a quick start example, so something that tells you, okay, this is an example that you can run, or these are the 5 steps or 10 steps that you can do to run something and maybe create some output, and this is what your output should look like, so that you know that it's actually doing the right thing, and then from there you can go and continue using the code. As you have seen in the repository we're using for this code, is you have on the right top side the possibility to link documentation, but you can also in the README basically point to longer documentation. Maybe you even have little YouTube files or so, or YouTube videos that show some introduction or so, and maybe there's a discussion forum where people can get help, or you tell them, please raise an issue. So you tell them also how to get in contact with you and how they maybe can contribute to your code base. So if you want to go full open source, tell them what you expect, what your code style is, or what you expect some code that they want to contribute and push to your repository can look like. And then you absolutely want to tell them who you are and how they can acknowledge you when they're using your code. License and also known issues, so that you don't get the same email again and again about an issue you know it's there but you can't fix now, is also very useful. And I want to talk about licenses in a moment, in, I don't know, half a minute or so, a little bit more. Just one more comment on this. So there are some files where the content can be in the README, but you might also put it into additional files that you can add to your repository. So, licenses. There are various, or there's a spectrum basically of types of licenses that you can use. So there are those where you say, yeah, take my code, take it away, no need to reference me or so, just do anything you want. And then there are those licenses where you say, like, no, actually it's mine and you can't use it. Some are copyleft. Copyleft means, okay, if you use my code, you actually have to use the same license I'm using here, so you can't go away and create a patent or sell this license or so, but you have to basically distribute any changes under the same license. And the licenses that we usually recommend or like to use are something like the MIT or the Apache 2.0 license, which are permissive, or if you want to use a copyleft license, the GPL 3.1 is one that we recommend. And the nice thing about the MIT license is that it's very short, so you can basically, I don't know how I scroll here, but it's actually a nice and short license. We've got 2 minutes for F-strings.
2 minutes, let's go. Okay, so the last thing is sort of general principles. And again, we've got Python in brackets because this is not about Python code, this is about all code. And so the main thing, I can't remember how much we left in this, but the main thing I want to say is about removing magic numbers. What do we mean by magic numbers? These are numbers, floats, integers in your code that exist as a 2.697 without any explanation whatsoever, which are great when you write them at the time. You know what you put into your Google calculator to get the number 2.697. But sort of 3 months down the line, you sit there wondering, what the hell was this? So the problem with these, like we say, they're hard to maintain. They're also hard to adapt. I'll explain what I mean by that in a moment. And they make code hard to read. The solutions to this, like many things, like we said with kind of explaining variables earlier, is to put these things into a variable that conveys its meaning. So when you come back and see, why have I got, I don't know, 273, 273, we know what it is, but you've actually said T0 or absolute zero. And then, yeah, the other option is to set a constant. And then the final thing, if you really, really need to use a number in your code, if it makes sense, and there are some instances where that is the case, this is the perfect time to use an explaining comment, as Marion mentioned in our last section. It's going to be too small. So the example I've got here is some code that's implementing the pendulum equations. Everyone knows the pendulum equations. So here we are. We've got our first magic number, 9.81. We're probably happy with what 9.81 is. We did physics courses. But can anyone suggest why it might be a problem as we look down that code? I'm thinking about reusability. Yeah, Nolan. Right, exactly, yeah. So this is great. We've got pendulum equations on Earth, 9.81. Suppose we give this to a colleague who's studying, I don't know, Mars. And they say, well, I want to be running my equations for a pendulum on Mars. We need an entirely different, a different gravitational constant. So we start going through and we say, oh, okay, that's fine, we'll retype it in here. But also we need to retype it in here, we need to retype it in, maybe that's all it. So we go away and run our code. Well, hey, we forgot to type it in here. So we're getting code that's running incorrect. And yeah, we could find and replace. So the better solution is to implement that as a single constant at the top of the file. Now you can see everywhere we've just got this one constant, grav, for gravity, and we set it at the header. If we want to change this throughout the entirety of our code, we just need to change it in one place. Similarly here, so we've got something that's checking the small angle formulae. Previously, this was kind of a slightly unclear what's going on, but by setting it in a variable, and this is very similar to what Aim was saying earlier, we've actually improved the readability and the interpretability of the code. And then finally, like I say, sometimes there's no way to get around this. It doesn't make sense. We're using this number in one place in one function. We don't want to create a constant somewhere else in the file at the top that we have to go tracking for. In this instance, it does make sense to use a magic number here, but so that someone understands when we come back to it, let's drop a comment just so we know why it's there. So I'd encourage you when you're writing code to go through and look for your magic numbers and have a go at removing them. And indeed, that's what exercise 6 is doing. And there's a particularly egregious example that I'll just pull out here, which is possibly anyone else who's working in convection will know this one. Often our models will output precipitation with millimeters per day. Sorry, we'll output precipitation in kilograms per meter squared. We're using SI units. But when we're looking at these things on a practical level for plotting, we use precipitation in millimeters per day. And the conversion of this, and I'm not even going to bother to try and remember it for you, I'm just going to go and look in the answer, is that this is a density multiplication combined with a time multiplication. So we've got 60, 60, 24 to get seconds per day, and then we've got the unit conversion is sort of magically hidden because it turns out 1 kilogram per meter squared is the same as, where have we got? 1 kilogram per meter squared is the same as 1 millimeter of rain. And I'll let you do the exercise to do the unit conversion. But without that in there, we're left with this 86400. Where on earth does it come from? As I say, it's a particularly difficult conversion to remember off the top of your head. So why remember it? Stick it in there. And with that, I think, yeah, there's a few of the things that you can look into. We don't cover them today, one of which is typing, and Dominic will have a session on that tomorrow. Next one, it's time is a blur. And so I'll just finish off by passing over to Marion, who's going to give you some parting comments.
So, just to reiterate, and we keep reiterating this because we keep hearing, oh, I didn't know about this, is if you need help with any of this, or you're doing the exercises in your own time and you're stuck somewhere, you wonder why something is like that, our ICCS RSE team is happy to help, and we have these climate code clinics, so you know that we have the spreadsheet for this week where you can put in to a slot basically when you want to talk to us. But we also have the climate code clinic anytime throughout the year, so we have an online form that you find on our website, and you find the link here in the slides as well. You can just put in basically, oh, this is the rough problem that I have, and these are basically the skills that I would need. Can I please have a time with an RSE? And we will come back to you and send you an email and arrange a time to meet with you and to discuss your problem, and then maybe discuss whether we want to basically meet again and basically have an iterative process of improving something or solving a problem, or whether you want to put in a resource allocation request to have a longer term project over several months with 1 or 2 RSEs. Yeah, if there's anything, please talk to us, use this form. Here are some additional links, and so and of course you've got the slides. There are always these footnotes and so as well. And if you want to contact any of us, these are our contact details, and these are the references for various bits and pieces that we've presented. Now it's coffee. Thank you.